So our next speaker is Damir Dzhafarov, who is going to talk about some questions and observations about the structure of Weihrauch degrees.
Okay, thanks for Ludovic. Thank you very much to the organizers for inviting me and for putting on this this really nice conference. Really wish I could have come in, made it in person, but it was just a little hard to organize. So it's nice to be able to attend at least like this. So thanks for making that possible too. Yeah, so this is a talk that's going to, as the title says, feature some questions and sort of observations. It's going to feature some kind of work in progress, and it'll also have some kind of older results that I think feed into the overall project. So the kind of newer stuff that I'll focus on towards the end is all joint work, very much in progress with Manny Lerman, Ludovic Pate, and Reed Solomon. Okay, so I'm going to give quite a bit of background at the beginning, which I think some of this may have come up at various other talks earlier, and I know will probably come up again, say in Arno's talk, which I guess is tomorrow. So let me do that though, just to kind of be self-contained and so that everybody's on the same page. I'll start with just a little background here on mass problems. So this is kind of maybe the background against which this talk should be set. I'm not focusing on mass problems. I'm not going to be speaking specifically about Medvedev and Muchnik reducibility, but I think it helps to frame the discussion. So partly because this is a much older kind of line of inquiry and a lot more is known here. So a mass problem is just a subset of Cantor space or Baire space. There is a difference in certain aspects, but for a lot of things, these are kind of interchangeable. And then the idea is that a mass problem, right, represents a collection of sets, which you can think of as sort of a collection of solutions to some kind of problem, some kind of mathematical problem. And there's many examples, and you know, there's I think these are familiar to us, right? But the PA degrees, you know, one random sets, things like this, these can all be somehow presented naturally as mass problems. Of course, in this setting, anything can be presented as a mass problem, but even certain kind of more natural restrictions allow for the presentation of lots of different kinds of problems. And I'll mention these restrictions a little later on, so I'll come back to this. But the main point here is that we can compare these mass problems under some kind of natural computability theoretic reduction. So we have Medvedev reducibility and Muchnik reducibility. So if we have two mass problems, C and D, C is Medvedev reducible to D if every element of D uniformly computes an element of C. So you have a fixed Turing functional, and if you apply that to any element in D, in the top problem, the bigger problem, then you get as an output an element of C. And C is Muchnik reducible to D if you have the same thing, but it doesn't have to be uniform. So the functionals can depend on the particular element of D you're working with. The aspect of this that will be relevant to what I want to talk about is that there's all kinds of interesting algebraic operations that have been looked at in this context. And in particular, there's meet and join operations. So these are lattices. And there's been a lot of work studying the algebraic structure of these lattices, their ordering properties, various other kinds of aspects. So here's just, you know, a highly incomplete list of people who have worked on it. Lots and lots of people have contributed results. And if you're in the audience and not on this list and should be, I profusely apologize. This is just a kind of smattering. So, okay, a smattering of computability theories. Okay, so let me come to what I do want to talk about, which is instant solution problems. So we have mass problems on the one hand and instant solution problems on the other hand. And for me, these will be the problems that I'm actually kind of focusing on, right? So the motivation here is, you know, you're coming from computable mathematics or from reverse mathematics, and there you're looking at theorems that have this general kind of shape, right? So for every x with some property phi, there is a y with some property, let's say theta with respect to x, right? So here typically, again, x and y can range over elements of Cantor space or maybe Baire space, and phi and theta are some kind of properties, maybe arithmetical predicates. And we think of this as a problem. So the problem is, given x satisfying phi, find a y satisfying psi, right? So the x's such that phi of x holds are called the instances of the problem. And given an x, the y such that psi of xy holds are called the solutions to x. So, say virtually every problem one looks at in reverse mathematics, with some notable exceptions, has this kind of shape, right? A slightly different way of kind of just phrasing this in computable analysis, one thinks of, say, partial multifunctions on Baire space, and the notation there is this one, right? P subset omega to the omega, arrow omega to omega. So you think of, this is actually now a function, and you give it an element of here, and it outputs it outputs possibly multiply many things in here. Okay. And we don't have to just restrict to Cantor space or Baire space. We can, in general, deal with other kinds of domains and codomains via various kinds of representations in terms of Baire space or Cantor space, right? So I'm not going to talk about represented spaces really at all, but if you want to talk about more elaborate kinds of settings, you can, and a lot of this discussion just transfers over very nicely. Okay, so as we did sort of have, as we had kind of Medvedev reducibility, Mushnik reducibility, there's ways of comparing problems in this setting. So the kind of analog of Medvedev reducibility is Weihrauch reducibility, which goes back to maybe the late 80s, early 90s to work of Weihrauch, and then was really developed by Brodka and many others, and was a few years ago kind of independently rediscovered, or sort of maybe I should say kind of discovered out of ignorance in this 5-way paper of ours, where we weren't aware of this notion, but kind of came to use it as well. So if, let's say we have P and Q, which are problems, so these are these kind of instant solution problems, or if you like, multifunctions, then we say that P is Weihrauch reducible to Q if, right, it's better just to look at the picture. So you give me an instance X of P, the problem to be reduced. From it, you uniformly compute an instance X hat of Q. And now if you give me any solution Y hat to this instance X hat of Q, right, so this is a solution in the sense of Q, then Y hat, together with that original instance X, uniformly computes a solution Y to the original problem, right? So it's a kind of uniformly effective way of reducing the problem P to the problem Q. And this fact that you are joining with the original instance is important in many applications, and I'll talk about this in a second. What happens when sort of you don't allow that. But you can think this is some kind, there might be some kind of cleanup process. You need some kind of post-processing you need to do to this in order to get a solution. So that's Weihrauch reducibility, and that has a non-uniform analog, just as Muchnik reducibility is to Medvedev reducibility. This was kind of first isolated and developed in these papers down here. So P is computably reducible to Q, written PC below Q, if we have the same situation as before, except now we drop the uniformity, right? So every instance X of P computes an instance X hat of Q. If you give me any solution whatsoever Y hat to that, then together with X, it computes a solution Y to the original problem. So this is a very natural notion of reducing one problem to another in computability, and of course it's implicit in a lot of work in reverse mathematics going back years and years. So this is a standard way kind of comparing problems, let's say these kind of instant solution problems in computable math. There are these strong analogs which now go to this issue of whether or not you allow joining with the original instance, right? So in both these cases, Weihrauch reducible and computable reducible, we also have a strong analog which simply denies access to that original instance, right? So now you have an instance X, it computes uniformly in the case of Weihrauch an instance X hat of Q, and now any solution to that must now on its own uniformly compute a solution to the original problem, right? And so here we have the uniform analog, here we have the non-uniform. So this is another variant, and many examples of reductions between kind of natural problems and that show up in computable math or in reverse math, in fact, exhibit this stronger notion, right? I mean, one relatively common situation is when this backward reduction is just the identity, right? So every solution x to x hat simply is a solution y to x, right? That can happen and doesn't happen that rarely. But other kinds of reductions do require access to that initial instance, and provably so, right? So we have a kind of several different ways of comparing the strength of these instant solution problems. And my interest here is not to present new results about different problems under these reducibilities, but rather to focus on these reducibilities themselves, right? To say something about them. So as with Muchnik and Medvedev reducibility, there are various natural operations you can define here. So here's two of them. So we have this I don't know how you read this square cap symbol, but what this is the following problem. So this p cap q problem is, its domain is just the Cartesian product of the domains of p and q. So an instance of this problem is a pair, right? It's a pair with an instance from p and an instance from q. And a solution to such a pair is a solution to one or the other problem in its one or the other instance relative to the problem it came from, right? So you give me an instance of p and an instance of q, and I have to solve either the instance of p as a p problem, right, or the instance of q as a in the problem q. And this is a disjoint union, so just kind of for bookkeeping, we indicate also which one you're solving, right? So you say, okay, I'm going to solve the p problem, and here's a solution. We also have the square cup operation, which is a little different. So now we have the instances are just the instances of p and the instances of q, disjoint union of them. So you indicate which one's which, where you're coming from. And a solution is just a solution, right? It's a solution. If you give me an instance of p as an instance of this new problem, then you have to solve that as an instance of p. And you also just indicate back that, hey, I'm solving a p problem, right? And similarly on the q side. Okay, so you give me an instance of q. So this is the instance of q. This is marking that it's an instance of q. And now you have to solve that. Okay, so these are pretty natural kind of ways of forming new problems from old. Actually, they're not that different from the kind of natural operations for join and meet in the Muchnik and Medvedev degrees. And indeed, these do give us the join and meet in the Weihrauch degrees. So Pauli and independently Brodkin-Gherardi showed that this square cap operator is the meet operation in both the Weihrauch and the strong Weihrauch degrees, and this square cup operation is the join operation. And actually, if you examine those proofs, both of these also hold in the computable and strong computable degrees. So the uniformity isn't really being used in an essential way. So what we have is that the Weihrauch degrees, computable degrees, and strong computable degrees actually are lattices under these two operations. This as the meet, this as the join. But what sort of came from this work was that the strong Weihrauch degree. So if you have strong twists one arm behind your back and Weihrauch twists the other one, right? They both kind of deny resources in different ways. If you deny both of them, then this over here does not seem to be the join. I mean, I'll say on the next slide why. And so all that kind of came out of this work was that for the strong Weihrauch degrees is that they form a lower semi-lattice, right? So we have meets, but we don't have joins. This doesn't seem to be the join. And in fact, that's probably so. So Brodkin and Pauli later showed that that this is not the join in the strong Weihrauch degrees, and motivated by that, several people asked, is there actually a join in the strong Weihrauch degree? What does it look like? And maybe just it's informative to say to kind of look at why does this not work? So let's just look at an example here. Suppose you have, right? Suppose you have something like problems P and Q, and both of them are Weihrauch reducible to some third problem R, right? So P is Weihrauch reducible to R via these two functionals. Q is reducible to R via these two functionals. So what might be a natural way to reduce this square cup operation to R, right? So the instances here are a disjoint union of the instances in P and Q. So a natural guess is that if you give me an instance that looks like this, right? I know it's coming from P by virtue of the 0, so I'm going to send it to this, right? Phi 0 takes instances of P to instances of R. So this will send me to an instance of R. And similarly, if I'm giving an instance like this, I know it's coming from Q, this x1, so I send it to phi 1 of x1. So I get an instance of x1. Now suppose you give me an instance of R, right? Now suppose you give me a solution y hat to this instance of R. How do we map it back? Well, you might say, okay, well, if y hat was solving a problem like this, I'll apply psi 0. And if it was solving a problem like this, I'll apply psi 1, right? And that doesn't work. And the reason it doesn't work is because you have no idea, just looking at y hat alone, whether it's a solution to something that came via phi 0 from the p half or whether it came from the q half. And what's even more is, right, you could have y hat that's a solution to both something that came from the p half and something that came from the q half, right? So somehow you would need to pick a side. And that seems really problematic, right? Now you face this problem that maybe you choose to somehow work on the P side always, but if this Q problem ends up mapping to something having this as a solution, you don't get a solution computed back in any reasonable way. So this kind of natural guess, which is exactly how you reduce in the case of Weihrauch reducibility, computable reducibility, or even strong computable reducibility, because there you can be non-uniform, so you can just make this determination non-uniformly. This is exactly how you do the reduction in those cases. This doesn't work in the strong Weihrauch case. Okay, so let me say how you do actually build the joint operation in the strong Weihrauch degrees, because I think they're an interesting structure in their own right. So let's define a monotone approximation to be a set like this. It's a set of triples of number, and a bit. And it's subject to some kind of nice monotonicity properties. So if we have NSI in A and NTJ in A, then S is equal to T and I is equal to J. So for each N, there's at most one pair of numbers like this so that the corresponding triple is in A. Also, if we have MSI in A and then TJ in A and M is smaller than N, then we'll say that S is less than T. So you can sort of think that, this is somehow enumerating information about membership in a set, right? It's saying N either is or is not in A, and we learn this fact by stage S. If you have that kind of view, then that's a good view, and it makes these conditions make sense, right? So 0 indicating it's not an A, 1 indicating it is an A. So this is just saying, you learn this at a definite stage, and this is saying that if you've learned it about some N, you should have already learned it about all the numbers smaller than N, whether they're in or A or not. But there's no condition that A has to be effective or anything like this. It's just a set of triples, right? And it also doesn't have to contain a triple like this for every possible N. If it does, we'll say that A is a total monotone approximation. Now there's a way of kind of evaluating a monotone approximation. So if you give me a monotone approximation A, I can sort of guess at the set it's trying to build. So what we'll say is that it's trying to describe, right? So we say E of A is all those N's, so that NS1 is in A for some S. Right? Okay, so it's this is what we would expect. And E is just a Turing functional, right? E takes reals to reals. It takes reals to reals provided this monotone approximation is total. If the monotone approximation is total, E will give you a real back. Okay, so how does this actually relate to anything we might care about? Well, if you think of a Turing functional C, then there's a kind of canonical monotone approximation that corresponds to it. We'll call that a sub c of x. So right, if cx of n converges and is 0, 1 valued, then this happens in some finite amount of time. We'll let s be the least amount of time that's needed for that, just the use of this computation, or the length of the use, depending on if you think of it as a time or a set. And then we enumerate NSI into this set, right? So it's exactly sort of according with that motivation we had up here of what a monotone approximation is kind of representing. But the key thing here is that whether or not C is defined everywhere or 0, 1 valued or not, a sub c of x, this monotone approximation, is always an x computable set. It is always a set. It's not, we don't get any kind of partiality or anything like that. It's an actual x computable set. Right? So it's an element of Cantor space. And just if you kind of follow normal use use conventions, right? Like if a functional converges on a number, then it already must have converged on all earlier numbers or something like that. Then these kind of conventions will just ensure that this is always a monotone approximation. Otherwise, you can just bake it into the definition. Okay, if C is total, then and 0, 1 valued, then what happens when we apply this evaluation functional to this monotone approximation is that we just get the real outputted by C. Okay, that's the kind of connection. Okay, so this is a kind of technical device, but what it allows us to do is to define the join operation. So here's the join operation. So suppose P and Q are problems. So we're going to define this square box operator. Its domain is just like the square cup, just like the join in the Weihrauch degrees. It's just a disjoint union of the domains of P and Q. So an instance of this is either an instance of P or an instance of Q, and you know which. And then what are the PQ solutions to something of this form, 0x? So that means x is an instance of P. Well, they're all pairs A comma S, where S is whatever you want, any kind of real. And A is a monotone approximation that evaluates to a solution of X, right? So X might have many solutions, and accordingly, there are lots and lots of different monotone approximations that evaluate to those different solutions, right? So here just we want some monotone approximation whose evaluation with this EMAP is a solution. And analogously on the other side, but symmetrically, if you give me an instance X of Q, right, then the solutions are things of this form, S, anything, and a monotone approximation A that evaluates to solution to X as an instance of Q. Okay, so if we now go back to this example of P being Weihrauch reducible to R via these two functionals, and Q being Weihrauch reducible to R via these two functionals, right? Remember that we had a seemingly good idea for, given an instance of the join, where do you map it to? Well, you map it to either phi 0 of X or phi 1 of X, depending on is this first bit is 0 or 1. But now if you give me a solution Y hat to this R, to the corresponding R instance that you get in this way, you no longer have to guess or speculate about where it came from or worry about that it may have come from both an instance of P and an instance of Q. What you do is you just say, okay, well, let me apply psi 0 to it, and let me apply psi 1 to it. If it actually came from an instance of P or Q, then one of these two things is actually going to be a total. And let me look at the corresponding monotone approximation, right? If it came from C, then this will be a genuine monotone approximation that evaluates to this. And if it came from Q, then this will be a genuine monotone approximation that evaluates to this, right? And if it didn't, then this will just be some set, and we don't care what it is. So this works, right? This is the nice thing. And so indeed, you can show that this is the join operation under strong Weihrauch reducibility. And in fact, so the strong Weihrauch degrees are a lattice. They're a lattice under the square cap and this square box operation. And it's fairly easy to see that if you look at any of the other degree structures we've looked at, Weihrauch degrees, computable or strong computable, then this agrees with the old joint, the square cup, right? So they are. It's not like it's giving you some kind of different lattice structure on those other structures. So it's nice in that sense. Okay. Yeah, I think maybe I'll skip this in the interest of so if you're actually dealing with partial multifunctions of represented spaces, there's also a natural kind of representation you can cook up so that that makes the square join, or whatever the strong Weihrauch join, be a partial multifunction of represented spaces, and it behaves nicely with that. But I think I'm gonna skip this in the interest of time. This is really kind of more for connoisseurs. So I'll move on. Yeah, and I think more interestingly, in some senses, is to look at distributivity now. So again, Pauli and independently Brodkin-Gardy show that the Weihrauch lattice is distributive, and they weren't looking at the computable or strong computable lattices, but the same proof. Their proof just works also for these other reductions. But somewhat surprisingly, and maybe kind of, you know, I mean, certainly seems a little strange, the strong Weihrauch lattice is not distributive. So it turns out to be not distributive. So the underlying logic of these reducibilities is actually different. Particularly the strong Weihrauch lattice is not isomorphic to any of the other lattices we're looking at here. So something again about, you know, you can deny one of the two resources, uniformity or access to the original instance, but when you deny both, the logic gets weird. So that's one of the motivations for looking at the algebraic structure here, right? Is to understand how these kind of relate, right? It is worth pointing out that this is not an indication of the strong Weihrauch lattice being somehow feeble or not very interesting. So it's known that the Weihrauch lattice, that the Medvedev lattice reverse embeds into the Weihrauch lattice. And the Medvedev lattice is known to embed every countable distributive lattice, for example. So there's a lot of richness, and that works for all of the lattices we're talking about, including the strong Weihrauch lattice. You can still reverse embed the Medvedev lattice into any of these structures. So there is a lot of richness, at least in terms of having a copy of the Medvedev lattice inside. Okay, so what we wanted to look at then in some of the kind of newer work was to try to understand more structural features, more about the algebraic content of these lattices. And you know, sort of one point of comparison that you keep coming back to is Muchnik and Medvedev, and thinking, well, you know, there's a lot of similarity on the one hand, right? And you might sort of think that a lot of results will simply lift from the Muchnik and Medvedev setting, which again has been analyzed far more extensively, to this setting. And that's true in a certain sense sometimes, but not always. And in fact, things get quite a bit well, more complicated, not necessarily in terms of proofs, but more complicated just in terms of setting things up. So and the fact that some of the proofs just don't hold. The results are different, right? So let me say something about that. So let's look at you know, maybe an initial point of comparison. So if we look at just the Muchnik degrees, and I'm going to look at all the Muchnik degrees. I'm not going to restrict to pi01 classes or anything like that, but just in the Muchnik degrees, right? If you take a minimal Turing degree, then the singleton M is a minimal Muchnik degree. And so you have something like, you have minimal degrees in the Muchnik degrees. On the other hand, in the Weihrauch and computable lattices, there are no minimal degrees. So let's look at this proof, because I think it illustrates sort of part of what the complication here is. The complication is exactly this fact that you have an interaction not only just between sort of classes of reals, but pairs of classes of reals, right? You have to do computability on the side of the instances and computability on the side of the solutions. So suppose we have a non-zero, non-trivial Weihrauch problem P. So if you sort of think about it, right, what is the trivial problem in the Weihrauch lattice? So a natural guess might be that it's one that has computable all the instances are computable maybe, and all the and solution is just the identity, it's the identity problem on the computable sets or something like that. That's not true, right? Because if you have a problem that has no computable degrees, no computable instances, then this particular problem will not be below it, right? So if you want a genuine zero problem, it can't have any instances, right? If it has any instances, then you could take a problem that, fix an instance X, take a problem whose only instance is X jump, right? Now this problem is not below this other problem, right? So if you want to have the zero problem, it actually has to be a problem that has no instances. Okay, so it has an empty domain, if you're thinking of it as a multifunction. So in particular here, if we're looking at a non-zero problem, it has at least one instance X. Okay, so now let's build a problem between it and zero. So let's define Q. The domain of Q is X jump, and it has the same solutions as X has in P. Okay, this problem is strictly in between P and Q, right? So in fact, P is not even computably below Q, again, because for P to be below Q, first and foremost, X, this particular instance, X has to compute some instance of Q, and it can't compute any instance of Q because X jump is the only one, right? But X jump uniformly computes X, of course, and then given any solution to P, right, we get a solution to Q just by the identity map. And since Q has at least one instance, it's also strictly above Q. Right? So we have, the situation is different here than in the Monotonic or Medvedev degrees. Things get kind of more complicated. But even this kind of initial toy example, right, shows that illustrates this fact. Okay, so the other thing we wanted to look at a couple different kinds of constructions, and we just realized, going into this, that we did kind of a lit search, and we emailed Arno and Vasco, and we kind of asked, and we asked, what's known, what's been looked at, and lots of things have been looked at, right? I mean, it's been asked whether the Weihrauch degrees form a Brouwer lattice. Is there, is it residual? Is it this? And lots of things are known, but on the other hand, a lot of basic questions weren't known, at least to us, right? And we sort of thought about, well, this should be obvious by applying this or that. And we realized that we actually don't know how to do a lot of these things. So one thing we didn't even know is, for example, if you have a problem, how do you always in some nice way always produce a problem which is incomparable to it? So here's how you could do it. And again, this proof is not that difficult, but let's look at it because it has some interesting features. So if you give me a countable sequence of problems P0, P1, then there's a problem Q which is incomparable with all the PI. And let's do under computable reducibility here. Everything I'm saying is so far is interchangeable, computable, or Weihrauch. But so here's how we'll do it. So for each one of these problems, choose one instance. Okay. Obviously, there should be an instance, because for us to be able to find something incomparable, none of these better be the zero, right? So I should say these are non-zero problems. These are strictly above zero. So they each have at least one instance. So pick one. And let's let I be the join of their jumps. It's countable sequence. We can do this. Now let's fix this I, which is a somehow a strong set, and let's look at all the I computable instances of PI for each I. So xi0, xi1. This might be a finite or infinite list. It in particular includes xi, right? The instance of PI that we picked. But it might include lots of others. Okay, so for each I, xi0, xi1, etc., are all the I computable instances of PI. Okay. Now for each I and j, let's let yj. Let's pick a solution to each one of these. So yij is a PI solution to xij. Okay, so for each one of these listed instances, we've chosen one particular solution. There may be others, right? Okay, so this is a countable sequence of sets. So we can pick something that's not only above I, but also above all of these yij's. This should be lowercase. I guess I changed notation at some point. So this should say y sub ij. So what is Q going to be? A problem. It's going to have the instance I, and it's going to have and its solution is going to be y jump. right? So this set high, which is above all of these instances. So the claim is that Q is incomparable with all these PIs. So none of the PIs can be reducible to Q, because they each have an instance, this instance xi in particular, right? And the only instance of Q computes the jump of xi, right? So xi can't compute I, and therefore can't compute any instance of Q, because Q has just this one instance. On the other hand, if you give me, if let's say I compute some instance of PI, let's say it's this one, then we know that this has this y, has a solution yi1, and that cannot compute y jump, because y is above all these things, and y jump is above, in particular, above yi jump, right? So this cannot compute any solution to this. So in this way, right, again, using both in a central way, using both the instances and the solutions, we've obtained incomparability. So every problem has a problem strictly above it. By, if you take joins, you can now get some basic facts, right? You can form incomparable problems, and by taking joins, you can go up. So basic features. But this is an interesting proof, right? It's an interesting proof because of the word choose here, and I guess the word let here, right? So we're using heavily the axiom of choice here for bare space, and or Cantor space, depending on how we're thinking of this, and that raises kind of an interesting question, right? Which, because you sort of think, well, we're doing computability, we're this should be sort of independent of maybe some kind of considerations of this kind. But you could ask, right? I mean, is choice really necessary here? These are collections of reals, right? So we're quantifying over subsets, over sets of reals here. So these are complicated statements in principle, and so it's difficult to see how you could get some kind of like absoluteness to help you or anything like that. So it's conceivable that maybe in some choice-free axiomatization of set theory, this result fails, and that would be interesting. And it's known that these issues do creep up. So one place where they creep up is with respect to having a top element in the Weihrauch lattice. So one way you can formulate the axiom of choice in bare space is to say that every problem has a realizer. So you have some kind of representation of if you like the problem in terms of functions from bare space to bare space. And it turns out, so Brodka-Empoli showed that the Weihrauch lattice having a natural top element is equivalent to the axiom of choice failing for bare space. Right? So in principle, some kind of choice considerations like this could be present also even in basic algebraic structure like we're talking about here. And there, I should say that, right, another way that you might think is if you don't subscribe necessarily to this kind of approach of thinking of these things as partial multifunctions, you take a more general approach, these are relations or what have you, then you might very well think that you could have a problem with instances but no solutions. And if you take a problem like that has computable instances, then you also get a top element in the Weihrauch lattice, right? So depending exactly on how you set things up, this is you can get different behavior here. And I guess there are different approaches to how these things can be defined. But here I'm just talking in the context of kind of thinking of these as actual multifunctions, right? So they are, if you give it an instant, if it has something in a domain, the function has to output something, right? Okay, so this was one thing. So then maybe we're studying kind of this global picture of the Weihrauch of these different lattices. Maybe we should go back to thinking about Muchnik and Medvedev results. So I want to kind of end with this discussion of something along the lines of restricting to natural cases, right? So with mass problems, there's a lot of interest in looking just at pi01 class, restricting to pi01 classes in bare space or Cantor space. So if we're looking in Cantor space, we use EW, ES. So this is a lowercase w, so not to be confused with Weihrauch reducibility. I thought about maybe writing something else here, but I think these are too standard to change them. or if you're looking in bare space, I guess people use SW and SS. For Medvedev is strong, right, and Muchnik is weak. And the reason that this restriction to pi01 classes is interesting is because most of the kind of natural examples that show up, where you actually want to look at them with randoms, PA degrees, whatever, these end up being pi01 classes. And at the same time, by restricting to pi01 classes, you kind of exclude some pathological cases that maybe you don't like, which what constitutes a pathological case. Maybe you might say, well, it has some properties as a lattice or as an order that are kind of unusual, or maybe they're not shared by the Turing degrees or other degree structures we like, right? So you might say, well, this behaves a lot more like these other structures that we've studied before. So there's all kinds of good compelling reasons to look in this setting. So is there something like that in the case of instant solution problems? Well, maybe is the answer. It's a little bit harder to kind of pin down. So certainly you can restrict to anything you like, right? But if you, for example, restrict to pi01 classes in Cantor space, you would lose a lot of natural examples, right? You would lose, for example, Ramsey's theorem for pairs, because the set of solutions of Ramsey's theorem for pairs are in particular infinite sets, and you have to say they're infinite sets. And if you lose Ramsey's theorem for pairs, which is such a locus of interest in say reverse math and computable math, maybe this is not the right restriction. You can also think of problems where restricting to pi01 would exclude it for reasons of for instances, right? I mean, so there are problems where not every real code's an instance, where you need pi2 definition of instances or something like that. So restricting too much excludes too many examples, and we kind of lose this first motivation, right? On the other hand, what's interesting is that maybe this actually is kind of nice to look at something like pi02. Maybe we don't have to go too far. Maybe we can just, pi02 already captures it. If we look at pi02, we get a Ramsey's theorem for pairs, but we lose, for those who know who these things are, we lose something like stable Ramsey's theorem for pairs and co. And I would argue that that's probably okay, right? These are kind of technical computability theoretic principles in some sense. Certainly combinatorially, they're not very natural. Combinatorially, they would be stated very differently. And so maybe looking at something like pi02, we would be the right level. But in any case, right? What I'm going to do is talk about the setting where we're looking at pi02 in Cantor space, or in fact, what I'm about to say will also apply to if you want to restrict to something like pi01 in the bare space. So within certain reasonable restrictions, right, we can try to see what are the algebraic properties of the Weihrauch lattice and the computable lattice. Okay, so the example that I want to kind of include here that I want to finish with is to look at density. So it's known that the Muchnik-Medvedev lattices are not dense as orders, and if you by a very different proof, but not hard to show, there exists. This is also true in the computable and Weihrauch lattices. So there exist strong minimal covers here, and therefore you don't have density. But what's interesting is that when you look into these natural restrictions, in the case of Medvedev and Muchnik, you do get density, right? So Senzer and Hinman showed that the Muchnik degrees are densely ordered, and then much more recently, Binz, Shor, and Simpson showed that the Medvedev degrees are densely ordered. Again, if we restrict to, this means restriction to pi01 classes, right? In Cantor space. In fact, I guess this also works for bare space. So one could say, well, let's look at the kind of restriction of the instant solution problems to some of these kind of natural, quote unquote, natural settings, or at least maybe what we're taking as a first approximation to natural setting, and see what we get. So let's let KW, now this is a capital W. So let's just for notation purposes, right? Let's let the Weihrauch lattice is restricted to problems where the instances and solutions are pi02 classes in Cantor space, and K lowercase c, this be the computable lattice restricted in that way, right? So instances and solutions are pi02 classes in Cantor space. Do we get density? And the answer is no, right? So even in this restriction here, we do not get density, and there exist strong minimal covers in both of these lattices. And it's important to point out maybe these are lattices. The meets and the meets and joints stay inside these restrictions, right? So these are not densely ordered, and so we have an algebraic difference. We have even if we sort of consider these to be the natural settings for instant solution problems, right? Algebraically, these are different. Okay. So that's a kind of surprising and I thought neat result that illustrates that there is something going on here, and maybe it's worth looking at. So let me give just a quick sketch of how this argument goes. Again, just largely to highlight that these arguments are quite different from arguments in Muchnik and Medvedev reducibility, because you really have to play off the instances and the solutions against each other, right? So here's a sketch. So we're going to construct a problem P and construct a minimal cover, a strong minimal cover Q of it under let's say computable reduction. Let's take a minimal degree below 0 prime and define P to have the following features. So the domain is every real, and then depending on whether or not a real is computable or not computable, the solutions are either, so if it's a computable instance, it's anything, everything solves it, and otherwise it's just M. M is the only solution. And now we're going to define I to be a different problem. I is going to have a single instance, it's going to be a sequence of all ones, and its only solution is M, this minimal degree. And we're going to let Q be the join of P and I. Okay, so Q is above I. But we claim more in particular that Q is a strong minimal cover of P. Okay, so here's the two problems again, just kind of restated side by side. Here's P, here's I, and so it's easy to see that right. I mean, P is clearly below P join I, but it's easy to see that P join I is not below P. So this is strict. Now, the key fact that I won't prove, but that this rests on is the following. So you can show that if P join I is not a strong minimal cover of P, then there's another problem J with the following feature. It has a unique non-computable instance X, and it lies between P and Q, right? This is Q, P join I. So you use a witness to you use a witness to the fact that P join I is not a strong minimal cover to construct this J. That's how that goes. Okay, and now we can do our argument to claim that P join I is actually a strong minimal cover. So suppose, right? I mean, there's two options. X is non-computable, and but let's look at its solutions, right? So sorry, this here says if J of X is computable, but what I mean is if J of X has a computable member, if X has a computable solution. There's a question here. 2 minutes left. Thanks, Ludovic. Oh, that was a direct message. I wasn't supposed to read that. Thanks. Ignore that. Okay, so if X has a computable solution under J, then we can actually just get that P join J is computable from P, right? This has a non-computable instance, so you can compute anything you want. You can compute any real you want. You can compute itself in particular, and sorry, you can compute itself, right? And then M will compute this solution to itself, to X, right? Because it has a computable member, so it's computable from anything you want. So that would give us a reduction of P join J to P. On the other hand, if J of X has an element Y, which is not computable, if it has no computable solution, then it has to have one which is computable from M and therefore of the same degree as M. And then you can get that P join I is computable to P join J. So so that would be the contradiction that finishes the proof. So we have density here, and in some sense, sorry, lack of density here, and in some sense, therefore, an interesting example of a structural difference, which seems to be preserved even under these kind of natural examples. Right? Okay, so with maybe -1 minute left, let me wrap up by listing a couple of questions, because as I said, this is kind of work in progress, and I think that there's a lot more to look at here. So you can really look at any of the kind of natural questions that come out of studying the algebraic or lattice theoretic properties of other degree structures in this setting, and most of them are open, right? So you can ask about splittings. Of course, you can ask about decidability and lattice embeddings, right? Which in particular, of course, Manny and Reed are very interested in. So we have some approaches on that. And again, these questions have been looked at in the case of Medvedev and Muchnik degrees, but there's very little kind of direct translation from that to this setting, as illustrated by these results. Can we find some other structural conditions that would show that these things are non-isomorphic? We have some examples here, but what else can be said? What's a good notion of naturality? That still seems to be open, and maybe there isn't a good one like there is for Muchnik and Medvedev, but that's something to think about. And then the final thing that we've sort of thought about is can something be said about the strong computable and strong Weierauch? I've been kind of focusing on Weierauch and computable. A lot of the results work also for the strong cases, but what other kind of features are present there? Okay, thanks. I'll stop there. Sorry to go over it.
Okay, thank you very much. Are there any questions?
Thanks, Damir. So this pi02 thing you're suggesting, is it pointwise? So I'm saying that for each instance, the set of solutions is pi02, or is it sort of uniform?
that's how we were thinking about it. Exactly right.
Okay, cool.
Yeah, but I mean, who knows? You could do something else too. You could have like a uniformly definable. I guess we thought about that maybe at some point too. Like you could maybe have like a uniform pi2 definition relative to the instance or something like that.
Okay, so Vasco has a question as well.
Yeah, thanks for your nice talk. So I have some doubts whether pi02 is really the real notion of naturality here. I mean, you should perhaps look at a notion that is preserved by the algebraic structure. I mean, there's more than just the join and the meet. There are implications, multiplications, jumps, and so forth. So I doubt that pi02 is preserved by those. And so how about Borel or something like Borel?
Right. Yeah. So that's a good question. I mean, this was a kind of initial attempt, and I think that's a good attempt. I mean, a good point. And indeed, there's a lot of these, for the residual aspects of the lattice and all these things, these operations, which may very well be incompatible with pi2. Right? We didn't check those, and that would be a good, maybe a good starting point. But I mean, on the other hand, right, these things study somehow different aspects of the lattice also, right? So maybe they don't all have to be compatible, but yeah, it's a something to look at for sure. Thanks for the point. Yeah, it's we should look at that and see what a more natural or more kind of more encompassing definition would be. Borel might be good, yeah, but then maybe you can't do anything. I don't know. Maybe it's almost just like looking at the whole thing.
Okay, thanks.
Thanks, Vasco. Yeah.
So thanks. Another question from Arnaud.
Right. So one sort of obvious way how the Weihrauch lattice is sort of different from the other ones is that it's bigger. There are just more Weihrauch degrees. Your result seems to give basically directly that you can extend anything that you could reasonably to an continuously many incomparable Weihrauch degrees, but there's room for more incomparable Weihrauch degrees. Have you thought about whether you can make that happen.
No, that's a new idea to me. Thanks. Yeah, it's something else to think about. Yeah, maybe we can chat about that after. That's interesting. Because I guess the lattices are very big, right? No, yeah, I don't have no idea.
Okay, there is a question from Richard. So
yeah, so I want to ask on the other direction. So, I mean, if you were motivated by not being able to say infinite, have you thought about pi01 on bare space instead of pi02 on Cantor?
Yes. Well, we did in the sense that there is the proof that I just gave would also work for pi01 on bare space. For density, you mean, or for
Proof of which theorem?
Yeah, sorry.
Yeah, you had mentioned that the
density or the non-density theorem. Yeah, the non-density theorem would work for that too. But yeah, in general, that's a good point. That could be completely different things that happen there.
Yeah,
and it seems like maybe even more so than in the Medvedev and Muchnik degrees, this could be sensitive to the distinction there. So we know some things, but not. Yeah, I mean, it's just there's an awful lot to check. So. Yeah. Thanks.
Nice talk.
So there is another question.
Thank you also for the talk. I will start with a maybe stupid question. So you mentioned that you argue the existence of an incomparable problem to the some countable set of problems with the axiom of choice for the bare space. There is something other for the counter space, or just the same problem with the choice?
Yeah, I mean, I guess you would just have the same question, but for axiom of choice for Cantor space in that case. Yeah, the same. I mean, we don't have a more constructive proof for Cantor space or anything like that.
Okay, and the other thing. So you mentioned that despite the existence of some strong covering for the Weihrauch lattice with restriction or without restrictions, so that's they are not dense, but the natural restrictions give the density to this Weihrauch lattice with this restriction. Yeah. So,
yes. I think, yeah.
Why we cannot just repeat the idea for the lattice with restrictions? So what disturbs us?
You mean so if you wanted to just take the proofs from the Medvedev-Muchnik setting and adapt them in the computable or Weihrauch setting?
Yes. Why does it not work?
Yeah, I mean, that was the natural first thing we tried to do, because it's nicer to use somebody else's theorem than to have to prove a new one. But yeah, it seems hard. It's just because you have this interaction between the instances and solutions. If you're kind of constantly thinking, well, if the solute, maybe we can just kind of ignore the instances or something like this, and just work with solutions, and then it looks just like the you know, in the Medvedev or Muchnik setting. But right, if you're given, say, two problems and you're trying to build something between them, those instances could be contributing to the reason you have a separation, or they could be contributing to the, you know, so between two Medvedev problems, if you have one strictly below another, you know something about those two classes of sets. If you now have two problems and you're somehow saying, well, these are now my instances, then you know something about the instances, but you don't know anything about the solutions. Those could be, you know, these could be ordered in a sort of reverse way or something like that. So it just gets very complicated, and there was no clear way to kind of pull it back to the setting we're working with. It could entirely be that there's some simpler way to do it, and say the restriction to pi01 or something like that. We don't know.
So it's not obvious why it doesn't work, but it's not. It's known how should it?
Yeah, I guess we don't. I think that's right. Is that we did think about pi01 Cantor space for a little bit, but it's just it's a much less interesting structure. But if you look at, yeah, I don't think we know that. I mean, it could be that in the pi01 case, if you restrict to pi01 in Cantor space, then you get the same thing. I don't know.
Thank you.
but not in bare space.
Okay, thank you very much. There is another question.
Yeah, just a comment. Since this has been brought up by Arno, I mean, this is very much work in progress I'm doing with Alberto. So all results are very, very much partial, but about anti-chains, I mean, we know that in the Weihrauch lattice and, well, for what it matters also in the Medvedev lattice, there are anti-chains of size 2 to the continuum. So, I mean, this is already, I mean, this is partially answers Arno's question. And I mean, you can do quite a bit of weird stuff. So first of all, what we managed to build is a family of 2 to the C chains. Each chain as size the continuum. No chain as an upper bound in the Weihrauch lattice. And all of these chains are like mutually, eventually incomparable. So, I mean, it's kind of like
I see.
a weird picture, I would say, right?
Yeah.
It's just a comment, right?
No,
But
that's cool,
then again, this is very much work in progress also for us. So, yeah.
Good. Yeah. I'll email you. Yeah. Who is that that's speaking so that I know who to email?
Manlio Valenti.
Oh, hi. Hi, Manlio. Okay. Yeah. Great. Yeah. I'll email you. We should compare notes and see if there's some. Yeah.
Okay.
Thanks.
Thank you very much. Any last question? No. Okay.
The most
So
questions I've ever gotten at any talk.
okay. So let's thank the speaker again.
Thank you.